Welcome to lecture. We'll get started in just a second or so. Again, we're continuing lecturing, I think on chapter 9 it is. Limiting reagents and stuff like that. Again, a reminder, if you have any questions throughout the lecture, feel free to type them in. Again, the chat box, I'll be happy to get to your question when I see it. And again, we'll get started here in just a second. All right, so before we get started, grades I think should have been uploaded and everything. Just a reminder on the exam, I think I hit all the right buttons, so I think you should be able to see the exam, sort of the answers you entered, the multiple choice part, and all that, those type of questions. In addition to, if you look up your uploaded file for the exam, you should be able to view feedback where you can see where I could scribble on the page and wrote some comments and stuff like that. So just a reminder that the actual exam, though, if you look at it, questions will still be marked wrong from the computer. I can't change that, but I did go back through, hopefully most of you saw, and I adjusted both any answers that were given online that the computer graded, and then obviously the questions that you showed work for and all that, I adjusted, you know, all the points where I thought was appropriate. And as a reminder, obviously, like a normal exam, it's not just the answer that you give online, but it's also the work that you show for those questions that have work associated with it. So you do have to show all the proper work to set up the units, you know, dimensional analysis and all that kind of stuff. So that, along with, I think some of those other ones were updated as well. Some of those experiments people were asking about, I think, last week. So that should be pretty current, I think, obviously in terms of your grade, sort of where you're at. And that also was updated for the it was updated for the online homework as well. Yeah, so again, you have to look at both, not only the exam, but you also look at the uploaded file. And when you look at the uploaded file, you should see something there that says feedback. You want to view the feedback, and that should open up your uploaded file, and you should be able to see scribbled on stuff that I scribbled, and it should comments and stuff like that if you look at the work part that was uploaded. Obviously, for any question that was just answered online, kind of like multiple choice or something like that, I really couldn't give too much feedback on it, other than you could see it was either the right answer or the wrong answer. But if you're looking for more of your work, again, I think you could access it through the grade book. And when you click on that assignment, I think there's a little thing that will say like view feedback to the right, where it shows submission details. And when you click that, it should open up a box of what you submitted, and then you should actually see lines, kind of like what you see here on the screen. You should be able to see lines like that, and then comments and stuff like that should be made on that. So you should be able to see that. All right, any other questions on that stuff? Okay. All right. So where we were talking about is stoichiometry. So we got through sort of basic stoichiometry type problems, and remember, basic stoichiometry problems really have you know, kind of 4 steps. In any stoichiometry problem, you want to make sure that you start with a balanced equation, and the balance equation is really important because none of this works if the equation is not balanced. You want to make sure that you convert to moles. And the reason you want to convert whatever they give you to moles is because from that balanced equation, we use that mole to mole relationship, which are essentially the coefficients from the balanced equation. And then we do the stoichiometry part, which is the mole to mole relationship from the balanced equation. And then at the end there, will be in moles, and then we can convert to other units if necessary. So these are the four really basic steps for a basic stoichiometry problem where you're only really given information about one thing in the equation, be it a reactant, be it a product, you know, and you can figure out how much reactants you need, how much products you need. Now, limiting reagent problems are pretty much the same steps, except right around here, as we talked about towards the end last time, you need to figure out which one is the limiting reagent. And remember, limiting reagents are really important because limiting reagents are the ones that basically will run out first in a reaction. So the reason why limiting reagents are important is they basically determine how much product you'll make. And when we make that product, that is sometimes what is referred to as the theoretical yield, is how much product we should make. And it's the limiting reagent that always determines that, because essentially in order to make the product, for example, like the equation we got at the top of the screen there, in order to make that SF6 on the right hand side, we need the sulfur and we need the fluorine to come together basically to do that. And as soon as one runs out, for example, let's say the S runs out, then we no longer have enough to make any more products. So when you're trying to determine how much product you would make, which is the theoretical yield in most calculations, that is going to be solely really based on the limiting reagent. There's also the excess reagent, as we also talked about. The excess reagent you have plenty of, so the excess you have plenty of. And you'll actually have some of the excess reagent left over when the reaction is all done. Now, there's a lot of different ways that you could figure out the limiting reagent in a problem. We talked about one way again. There's are some other ways that you could do it. But one way that you could figure out basically which one is the limiting reagent, and sort of the nice thing about trying to figure out which one is the limiting reagent is the idea that if you could figure out the limiting reagent, you will know by default the other one is the excess, or vice versa. If you're able to figure out which one is the excess reagent, you could figure out which one is the limiting reagent. So for example, one way that you can basically do it is like what we see here at the bottom of the screen. And in the case, you could do one calculation to determine the limiting reagent. And basically you just pick one reactant. And basically what you're doing when you pick that reactant is you're trying to see how much of the other reactant you would need to put into that reaction to use it completely up. So if we look at down here, if we want to know how much sulfur is needed to use up all of the fluorine we started with, that is basically what this calculation is. If you remember from last time in this problem, we started with 20 moles of F2. And we started with, I think, 4 moles of S. So starting with our 20 moles of F2, using the equation, we see that there are 3 moles of F2 for every 1 mole of S. And that's what this part is. This is basically the stoichiometry, the mole-to-mole relationship from the balance equation. And we get this number here. And this number here represents how many moles of sulfur is needed. to use up all of the F2 that we would have started with. And what you want to do at this point is once you do this calculations, you want to compare it to your starting amount. So if you compare it to your starting amount, which was over here, what we see is in this calculation, it tells us that we need 6.7 moles of sulfur, but we're only starting with 4 moles of sulfur. So what that tells us is we do not have enough. And what that means is because we don't have enough, that means that this is the limiting reagent. Our reactant is sometimes called. And that would mean that the sulfur is the limiting reagent and the fluorine by default would become the excess reagent here. Any questions on that? So this is one way that you can pretty much determine which one is the limiting reagent and which one is the excess reagent. You then would do the calculation going back to your limiting reagent and using that to figure out how much product you would make. So that's one common way that you can figure it out. And then when you figure out that product that's made, that's your theoretical yield. Now, just to sort of highlight another way that you could do this in a very common way is you basically would do 2 separate calculations. You would start with the sulfur and figure out how much of the product it would make, so the SF6. And then you would do the exact same calculation starting with the F2 and figure out how much SF6 it made. And if you do that, let's see here. So another common way, like I said, would be to go back this way. We'll do it over here. Find some room here. Actually, I will. Let's scribble here. So another common way, I'll just write it towards the top. Another common way is to basically do 2 separate calculations and figure out how much product each would produce. And the one that produces the smallest is your limiting reagent, and that also would be your yield, your theoretical yield that you would make. So that's another common way sometimes limiting reagent problems are done. You basically just take each reactant individually, you do a separate calculation from that reactant to the product, and then you compare and see which one produced the least, and the least would be the theoretical yield, and that would also be your limiting reagent. So again, in your book, they may show you the problem that way, and that again is a very common way that you can do that. Any questions on how to do limiting reagent type problems there? Okay. So let's take a look at this problem here, and we want to figure out if we start with 6.83 grams of the iron plus the sulfur, and we go to and we react it with 9.34 grams of the sulfur. So 9.34 grams of sulfur, 6.83 grams of iron. How much product would we make? So let's take a look at this one together to sort of see how it all works. So I flip the page here so I got something to write on. All right. So if we look at this problem, we have Fe plus S goes to FeS, and we're basically mixing 6.83 grams of iron with 9.34 grams of sulfur, And we want to know basically how many grams of iron 2 sulfide would we produce. So the other thing that we talked about was how you could recognize that this is a limiting reagent problem. And the way you could do that is by the information given to you. So for example, we were given 6.89 grams of iron, and we also have 9.34 grams of sulfur. And we want to know how many grams of that guy. So in a basic stoichiometry problem, if you remember, like the ones we did last time, you were really only given information about one of the guys in the equation, maybe iron, for example, maybe iron 2 sulfide, maybe just sulfur. The key to know that this is a limiting reagent problem is you're given enough information about both of the reactants to calculate moles. It was 6.83. What did I write? I did. Thank you. Yeah. 3 is kind of like 9, but a little bit off. Thank you. It is 6.83. So the way you can realize that it is a limiting reagent problem is you have the ability to calculate the moles for both reactants. So that is the key. When you're given information about both of the reactants or all of the reactants, and you're able to convert that information into moles, that's how you know it's a limiting reagent problem. So if we were just given, in this case, the 6.83 grams of iron, and that's the only information we're given, it's not a limiting reagent problem. It's assumed that the iron would be the limiting reagent and the sulfur would be the excess. But in this case, because we are given the starting amounts of both reactants, we do have to find which one is the limiting reagent. Now, to do this problem, it's basically the same first steps. Step number 1 here, ready, done. We have an equation, and it is balanced. Step number 2 is convert what they give you to moles. So that is the first thing that we want to do here. So we're going to do that for both 6.83 grams of iron. We're going to go to the periodic table and look up iron, which should be 5585 grams per mole. We're also going to do the same thing for our sulfur, which is 9.34 grams of sulfur. Also going to go to the periodic table and look up sulfur, which is 3207 grams per mole. Again, a reminder that we typically do take 4 significant figures when we pull it off the periodic table. And if we do that, grab our calculator here, try to push the right numbers in, 5585. So if we do that for our moles of iron, we get 0.122. And for our sulfur, we end up with 9.34 divided by 3207 gives us 0.291 moles of sulfur. So the key here is that these two numbers are our starting amounts. So these are our starting amounts of each of these. And the next thing we will need to do is to figure out which one is the limiting reagent. So I'm going to do that calculation in different colors just to distinguish it. Grab a little green. So we need to figure out which one's the limiting reagent because we've already know it's a limiting reagent problem because both pieces of information was given to us. No, on most periodic tables, I think it rounds to 3207 for the molar mass for sulfur. I don't think it'll make that tremendous of a difference, but usually 3207 is kind of where it's at. Now, remember to do this calculation to figure out the limiting reagent. We want to pick one reactant, and it does not matter which one you pick. So I'm just going to pick the first one here. So I'm going to pick this guy. And basically what we're going to try to figure out is if we want to use up all of our iron, how much sulfur do we need? So that is essentially what we're trying to figure out is basically how much sulfur we need to use up all of our iron. So we're going to start with our starting amount, which is right here. So that is 0.122 moles of iron. We're going to go to the equation and find the mole-to-mole relationship between iron and sulfur, which in this case makes it pretty easy. It is a 1-to-1 relationship. So for every 1 mole of iron, and that's just the coefficient from the balance equation, that gives us 1 mole of sulfur. The moles of iron will cancel each other out, and that will tell us that we need 0.122 moles of sulfur is needed. Any questions on that calculation? Now, the 1.22 moles of sulfur is needed. What we then want to do is we want to compare the sulfur that is not clicking that button here. Let's go this way. There you go. We want to compare the sulfur that's needed to the sulfur we're starting with. So in terms of need, we need 0.122 moles. And in terms of starting amount for our sulfur is right here, which is 0.291 moles. What we're comparing is, do we have enough? And hopefully you can see that you only need 0.122 moles of sulfur, and you're starting with 0.291 moles of sulfur. You do have enough. And because you do have enough, what that means is that the sulfur is our excess reagent. And by default, that would mean that the iron is the limiting reagent. Any questions on that step there? So you just got to do a basic little calculation to figure out which one is the limiting reagent and which one is the excess. Again, as I mentioned before, you do not have to do the calculation for both reactants. You can, but you don't have to do it for both reactants. You just need to do it for one of them. Any questions on that calculation? Okay. And again, if you did the calculation for the other, it would be you would start with the sulfur and try to figure out how much iron you would need to use up all this sulfur. And what you would find is the same thing. You would find that you don't have enough iron in that case. Okay. Now, once we figure out that this guy is our limiting reagent and this guy is our excess reagent, the important thing is to now figure out how much iron 2 sulfate would we produce. So the important part is we actually want to make sure we go back and use our starting amount of our iron, which is our limiting reagent in this case. So we're then going to do the calculation using our starting amount, which is 0.122 moles of iron. Now in this case, what we're looking for is the mole-to-mole relationship between iron and the product. And between iron and the product, we see that again, there is, in this case, pretty easy. 1 mole of iron gives us 1 mole of our product. So 1 mole of iron will come here. 1 mole of our product will come here. Again, that's from the coefficients from the balance equations. The moles of iron will cancel. We will end up with 0.122 moles of iron 2 sulfide. Now, in this case, we're not interested in moles, but we're interested in grams. So we will need the molar mass here of iron 2 sulfide, and that would be from the periodic table. There is 5585 grams for the iron, plus our 3207 grams per mole for our sulfur, which if we add that together will get us 8792 if I added that right. Remember, we're going to use that to figure out how much product we're going to actually make. So when we do that, we will use the molar mass as a conversion factor, and the grams will go on top. And the moles will go on the bottom. The moles will cancel, and times 0.122 gives us about 10.7 grams of iron 2 sulfide would be produced. And this again is what is known as our theoretical yield. Again, you don't necessarily have to get an answer in between. You could go straight through from moles all the way to grams. Any questions on any of those steps? Yeah, so like a normal sort of calculation, pretty much you could consider everything in between. I'll come down here. So say everything in between from here to the end, almost as just conversions. So probably in most cases, what you want to do is go back to the original number. So our original number, if we looked at iron, for example, had 3 sig figs. So probably 3 sig figs on the rounding there would be what you want to go with. So usually in these sort of stoichiometry problems, probably whatever the starting amounts were given to you, and then whichever one you use, that's probably sig fig wise what you should end up with. Other questions on any part of that? Okay. Now, this is again the steps that you want to follow. We know that this was a limiting reagent problem because we were given the starting amount of both, and that's again how we know that. Now, another very common question is sometimes asked when you do these type of problems is, in addition to figuring out how much product you would make, you're oftentimes asked to also figure out how much of the excess reagent would be left over. So if we want to know how much of our excess reagent would be left over, we could also do that from this type of calculation. So in this particular example, what we've seen is our excess reagent, in this case, is the sulfur. And what we know is that we started with 0.291 moles of sulfur. That's how much we started with. And we did get lucky in this case, since we did this calculation here. That told us basically how much sulfur we would need to use in this reaction. And that means that we can subtract the 0.122 moles, which was what was needed. And if we do that, 0.291 minus 0.122 gets us 0.169 moles. And that's how much of sulfur would be left over. And again, if we want to know how many grams that would be, we could use the molar mass for just sulfur in this case, which is 3207. And that's from the periodic table. And if we do that, times it by 3207, gets us about 5.42 grams. Would be left over at the end of this reaction. So sometimes you're asked in these type of problems, not only to figure out the theoretical yield, which is how much you, in theory, should produce if everything went perfect in the reaction, which in this example is 10.7 grams of iron 2 sulfide, but sometimes you're asked to figure out how much of that excess reagent you would have left over. And as you can see here, we actually started with, in terms of grams, we started with about 9.3 grams of the sulfur. We would actually have about 5.4 grams left over. So we used probably just under 4 grams in this reaction. Any questions on any of that? Now, to be truthfully honest, if we did the opposite calculation up here, you would not have this number available to you, which means you would have to go and actually do this calculation. What I mean by the opposite one was if we did the how much iron we would need calculation, you would then have to do this calculation to figure out how much excess would be left over. So sometimes you get lucky, you choose the right one, but sometimes you might have to go back and do one additional calculation, which would be just like what we did here in the middle of the screen for the other reactant to figure out how much of the excess you would need. Any questions on any of those steps? Again, it's really still the basic stoichiometry steps, except that you have to do that little step in the middle there to figure out which one is the limiting reagent. Any questions on any of that? Okay. So let's see here. So this is the one we just did. I'm just going to scroll across the screen. That way you could have something to look at later if you want to go back and look at it. That's not so scribbly. I kind of typed out at one point. And again, it's the exact same steps that we just did a second ago. So I'll scroll through that so you can at least see it if you want to go back and sort of see that. Good news is I think they got the same answer, so that's always a good thing, I suppose. So that. All right. So why don't you give this one a go and see what you come up with. And yeah, I think I got some Molar Masses given to you and everything. Perfect. So why don't you calculate the mass of our product here and also see if you can figure out how much is left over when it's all said and done. So I'll give you 5 minutes or so to kind of work on it. And I think everything that you need's up there. The molar masses from the periodic table, so you don't have to look those up. So you should have everything you need. And then we'll talk about it, see how everybody's doing. I want you to take a couple of minutes here and give that a go and see what you end up with. Yeah, I'm actually not working out. I'm just writing everything up. I'm going to work it out in just a minute or two. Just getting everything written on the board. Sorry. But I'm going to go over everything and just kind of rewrite it on the screen. Yeah, so in terms of rounding like normal, you could round a little bit. Again, you don't want to round too extreme and kind of clean up at the end. But if you want, you can. If you're asking when you convert, say, from grams to moles, you could do a little bit of rounding at that point, I would say. Oops. I keep wanting to go to that screen. Make sure that. Okay, so let's take a look and see how we're doing on this one now. All right, here, just move a couple things off my screen so I can see myself. All right, so first off, in this problem, we're given an equation, and we do see it's balanced. We do see some numbers here, so it's probably balanced. That's good to start with. The second thing we see is we're given the starting amounts of the NH3 and the CO2 in this case, which again tells us we're given the starting amounts of both reactants. So that should again be a big kind of clue that this is a limiting reagent problem. So again, that means that we do need to at some point figure out the limiting reagent, but that again is how we know it is a limiting reagent problem. You pretty much are given the starting amounts of both reactants and you're able to kind of convert those into moles, which happens to be the next step that we want to do. We want to convert to moles. And again, we're going to use the periodic table as our conversion factor to do that. In this case, they actually gave us the molar mass from the periodic table of each of those. So we'll use that. So we're going to take our 622.7 grams of NH3. And again, if it was not given to you, you would go to the periodic table to get this number, the 1701. We would also take our 1241 grams of CO2. Also go to the periodic table and get the molar mass. And again, that would be 4401. And using our handy dandy calculator here, perhaps 622.7 divided by 1701 gets us something like, and again here, you can round if you like, 3661 it looks like, moles of NH3. And if we do it for our CO2, we will end up with 28.20. And again, a reminder that these two numbers represent the starting amount of each of the reactants that you have. Any questions on that calculation so far? So since we know it's a limiting reagent problem, again, you can choose either one of these guys. So I'm going to choose the NH3. So what I'm going to try to find out is how much CO2 is needed to use up all of the NH3 in this case. And again, to do this calculation, which is simply going to allow us to figure out which one's the limiting reagent and which one's the excess reagent, I'm going to take my starting amount of NH3. I'm going to go to the equation and use the mole to mole relationship between NH3, which is 2, and CO2, which is 1. And that means that for every 2 moles of NH3, I should have 1 mole of CO2. The moles of NH3 will cancel. So we'll take our 3661 divided by 2, basically. And in this case, we will end up with 18.31 moles of CO2. Again here, that is how much is actually needed in this case. Yeah, so it depends on the periodic table. So 1401 plus 3 times 1.008. It does give us 1703. Did I write the wrong number? I think you get a pretty close number if I'm not mistaken. Divided by 17.03. 3656, I guess. Pretty close. We'll change it then. Thank you. It is, I think I wrote the wrong number there. So that is 3, and I think it's going to make a tremendous difference here, but 17.03, 3656. Thank you, 3656 moles. And obviously this would become 56, and divided by 2, 1828, so pretty close to 18. Sorry about that, 1828 moles of CO2. Thank you for that. There you go. A little bit of scribble. There you go. All right, so 1703 is the molar mass there. I had that on my table, and I just wrote 1 for some reason. Any questions up to that point there? So when we have this number now, this again represents how much CO2 that we need. So we want to compare it so I think your question is, where did I get the 2 from here? Yeah. So that is the mole to mole relationship from the balance equation. So for every 2 moles of NH3, there is 1 mole of CO2 from the balance equation. Yeah. And the reason we needed that relationship is because this calculation that we're doing here, we're trying to figure out how much CO2 would be needed to basically use up all of this. So we want to use up all of it. So if we want to use up all of that first reactant, how much of the other guy we had to put in there. So that's where that came from. So what we want to compare now is we know that we need 1828 moles of CO2. We want to know, do we have enough? So we would want to take this and compare it to our starting amount. And what we see is that we started with 20 moles of CO2, and we need 1828 moles of CO2, and that means we do have enough. Any questions on that comparison? So what that means is because we do have enough, that should mean in this problem that the excess reagent is the CO2, and our limiting reagent would be the NH3. Any questions on that part there? And again, the purpose of that whole calculation we just did was essentially to kind of find that out. So now that we did find that out, to figure out how much of our product we would make, we now want to use our limiting reagent and figure out how much product we'd actually make. So using our limiting reagent, and again, not just using our limiting reagent, but we want to use the starting amount of our limiting reagent. So that means we would use our 3656 moles of NH3. And now what we're looking for is how much product we would make. So again, going back to the equation, we see that there are 2 moles of NH3 for every 1 mole of our product. So we're going to use that relationship. 2 moles of NH3, 1 mole of our NH2, 2CO. So again, we're going to divide our 36.56 by 2. We will get 18.28 moles of our product. And here we don't want just moles, so we do want molar mass. And again, they gave it to us in the problem, and I hopefully copied it right this time, 60.06 grams per mole of our product. And if it wasn't given to you in the problem, you would need the periodic table to find that. And if we times that by 60.06, we end up with about 1098 grams of our product that was produced here. And again, this would be what is known as the theoretical yield. Any questions up to that point? Now, the second part of the question was how much of the excess reagent would be left over. And again, here we did get kind of lucky. We could actually answer that based on the calculation that we did. So to figure out how much of our excess reagent is left over, so the reason we knew NH3 was a limiting reagent was from this calculation here. So from this calculation, using our starting amounts, we figured out that if we want to use up all of the NH3, we would need to put in there 18.28 moles of CO2. And upon comparing that to our starting amount, we saw we had enough of CO2. So what that means is because CO2 was the excess reagent, by default, our other guy would be the limiting. So that's how we were able to determine that. So the nice thing sort of about that calculation is you don't necessarily have to do the calculation for both. Once you figure out, for example, like we did in this problem, that one of them was the excess reagent, that means that the other guy would be the limiting, and vice versa. So if you did the calculation, you figured out something was the limiting reagent, that would mean by default the other guy would be your excess. Other questions on that? Okay, so part of this question was to figure out how much of our excess was left over. So in this case, our excess reagent, again, was the CO2. And in terms of how much we started with, 28.2 moles of CO2. And again, that comes from up here where we did our how much we started with. And we also figured out, because we actually did get a little bit lucky here in this calculation, we already had that number. Again, if you didn't do that one, you did the other one, you would then have to do this calculation to answer this question. You need 18.28 moles of CO2 is needed. And I have a calculator here, 820 minus 1828 gets you 992. That means we would have 9.92 moles of CO2 left over. And again, if we want to know how many grams that would be from the periodic table, we got 4401 grams per mole of CO2. And we will end up with, we'll call it 436.6 is left over, which you could check if you didn't mess up, because this number should obviously be less than the CO2 that we started with, which in this case, we started with like 1,200, I think, 1,241 grams of CO2. So out of that 1,241 grams of CO2, we would have about 436 that's left over. In terms of the CO2 would be left over. And then our theoretical yield there would be the 1,098. Now, like I said before, again, we got lucky in these couple of questions where we actually chose the right reactant to allow us to have this number. If you didn't, again, you would have to do this calculation before obviously you could get to this number. So you may have to do a additional calculation to sort of get that number. Again, you may be lucky, kind of like we were in these last couple of examples, that we sort of chose the right reagent to answer that, how much excess is left over. Any questions on any of those parts there? Okay, so let's see here. And again, this is what we just solved, so I'll roll it through the screen. So in case you want to look at it later, it'll be kind of printed out for you. Without all my scribbles, looks like we got the same answers, so I guess that's good. All right, any questions on limiting reagents so far before we talk about one extra thing here with it? And that is yields. So we've sort of covered a little bit about yields as we've been going through. And there's a few different types of yields. The first type of yield is what is known as the theoretical yield. And the yield in a reaction is basically how much product that you would produce. And again, there's three types of yields. The first one is the theoretical yield, and that really is sort of your maximum amount of yield that you should get. And that is really just based on the starting material and the starting amounts and the balanced equation. And if you do, just like we just did in that previous problem where we got the 1,096 grams or something like that, the amount of product that you should produce based on how much you start with and the stoichiometry from the equation is what's known as the theoretical yield. It is sort of your maximum amount that you yield. That basically means everything went perfect. You didn't spill anything along the way. You didn't lose anything along the way. Everything went perfect. No side reactions based on the equation and your starting amount. That's how much you should get. Now, number two is the actual yield. The actual yield is pretty much like the name implies. It is actually how much you produce when you physically go and do the reaction. So when you physically have done the reaction and you're at the end of it and you weigh it, for example, if you made a solid like in the experiment today, that is actually how much you would have produced. So the actual yield is usually smaller than a theoretical yield. It can be larger than a theoretical yield, but it usually means something went bad. So for example, the experiment that we're going to do today, the precipitation experiment, when you do it and you make this precipitate on a very badly looking filter paper, in case you can't recognize that squiggle. So if you had some filter paper with an L. And say we did precipitation reaction and we isolated this solid, for example, through the process of something. Usually when you do this, for example, it's usually a process of filtration that occurs. And as you would filter the solution down, what would be left on the filter paper would be this here. And just through that process, what usually will happen is the filter paper is still wet. So if you decided to weigh it right away, like right after you filtered it, you undo the paper and you weigh it, what you're going to get is usually a mass that's much heavier than just the solid because you have all that water weight that's on there. So you can get this higher actual yield, and it's usually a result of an error, something like that. And that's a very common error. If you sort of did that and you filtered it, this paper would still be wet, for example. And if you weighed it right away, all that mass that you think is the solid alone actually is the solid plus some water. So you got a lot of this water weight on there, which is why when you do a reaction like the one you're kind of going to do today, typically what you do is after you do and filter it and get your solid, you either put your solid in an oven to dry, or you let it dry out naturally to get rid of all that water, so that when you go reweigh your filter paper, the mass that you get is essentially the mass of just the solid. So that's usually where you can uh, end up getting a actual yield that's higher, and it's usually a problem. So if it is higher, it's usually not a good thing. Bad things happen, X's and things like that. Yeah. So you definitely don't want to usually get an actual yield that's higher. So when we talk about these yields, we oftentimes will put them together and calculate something that is known as percent yield. And percent yield tells us how good we did a particular reaction, for example. And usually percent yield near 100, good. In reality, it's usually not exactly 100, in the high 90s or above 90, ish. It's a bad 90 and above usually is pretty good. 95 and above is even better. But usually, again, not over 100, but anything less, if you get like 2% yield, again, not so good. That means you probably dropped a whole bunch of stuff all over the place. So to calculate the percent yield, you take your actual yield, which in book problems is usually given to you. So usually in book problems, that number is given to you. Your theoretical yield, which is usually in book problems, ones you have to calculate. Now, your theoretical yield could be a basic stoichiometry problem like what we did at the beginning when we were talking about this stuff, or it could be a limiting reagent problem like we did as well just recently. But somewhere along the way, usually you'll have to calculate the theoretical yield in a problem. And then, like I said, in a book type problem, the actual yield is usually given to you. And obviously, it's a percentage when it's all done. So you could do, in terms of percent yield, you could do grams divided by grams. You could do moles divided by moles. Those are the common ways to do it. Usually people go grams divided by grams, but again, as long as the units are the same, you technically can divide the top and the bottom by any unit you want. But grams over grams is typically the usual ones, or moles over moles you could do as well. Any question on percent yield? All right. So why don't you give this a go and see what you come up with, and then we'll talk about it here. So this is basically the same equation that we were just using in the last problem. Here we're going to start with 100 grams of ammonia and react with 100 grams of CO2. And if we did produce 120 grams of our product, we want to determine the percent yield. So why don't you give that a go? I'm going to flip the page and just write the stuff up, and then in about 5 minutes or so, we'll kind of go over it, see how everybody's doing. So we want to know theoretical yield and also percent yield in this case. Okay, so let's take a look and see how we're doing since we're getting to the end here. So again, in this problem, we're going to be mixing or putting together 100 grams of ammonia. It's reacted with 100 grams of carbon dioxide in this case. We're going to produce 120 grams of our product there, the NH2CO. We want to know what is the percent yield. So when we do look at this, again, like I said before in sort of book type questions, this is our actual yield. Yeah? And that is usually given to you in sort of a book type question or anything like that. Remember that our percent yield is the actual divided by the theoretical times 100%. So in terms of that, we already have the actual given to us. So we do need to, like in most cases, we do have to do the calculation here to figure out our theoretical yield. And that calculation, again, is going to come from the actual equation and how much we're starting with. So the other thing that we see is we have 100 grams of our NH3. We also have 100 grams of our CO2. I think I moved that previous question out of the way. So we're just gonna work on this problem at this point. So I'm sorry, in your notes, there might have been a problem before this one stuff. So we are skipping to this problem here that we're doing on the screen. So the other thing that we see is we have basically both of these given to us. So because we have both of the starting amounts given to us, we know that this is a limiting reagent type problem. So we do need to figure out the limiting reagent first along the way when we do this problem. So again, those are all the components. It's really a stoichiometry type problem, and it is a limiting reagent problem. And at the end, we're going to put it into our theoretical, our percent yield equation. So let's get going on that. So here, it's all the information. It was actually the same one that we did in the previous. So the first thing is, as we can see, we do have our equation and it's balanced. So step number 2, just like normal, we want to convert to moles, right? So we're going to take our 100 grams of NH3. We're going to use the molar mass, which is the same, and I'll use the right number this time, 1703 grams per mole of NH3. We'll also take our 100 grams of our CO2, and we'll use the molar mass. Again, if it was not provided to you, the periodic table is where you would get those numbers. Our grams of CO2 will cancel, our grams of NH3 will cancel, and that means that we will open up with 5.872 moles of NH3 and 2.272 moles of CO2. And again, a reminder that this represents your starting amount. Right? So because this is a limiting reagent problem, we need to do that extra little calculation to figure out which one is the limiting reagent. So as we've done before, you could pick either one of these guys to do that part with. So I'm going to pick, again, the first guy there. So I want to know how much CO2 is needed to use up all of the NH3 in this case. So again, we would start with our starting amount of NH3 because that's how much we want to know. We want to use all of that up. So for this calculation, just like what we did previously, we need the relationship between NH3 and CO2, which is again a 2 moles of NH3 gives us 1 mole of CO2. The moles of NH3 will cancel each other out. And 0.2936 looks like. I read that right. No, I did not. I'm bad with numbers today. 2.936 moles of CO2 is needed. So remember that this number here that we just calculated, we then would want to compare to our starting amount. And in this particular case, we started with 2.272 moles of CO2. We need 2.936 moles of CO2. We do not have enough. So because we do not have enough, what that tells us is in this problem, the CO2 is the limiting reagent, and by default, the NH3 would be the excess reagent. Any questions up to that point there? So once we've determined that our limiting reagent in this case is the CO2, we then want to actually do the calculation to figure out how much product we would produce. So to figure out our product, we would start with the limiting reagent, which is 2.272 moles of CO2. To figure out our product, again, we're going to go back to the equation. And for every 2 moles of NH3, that's the wrong relationship there, bad. For every 1 mole of CO2, we get 1 mole of our product. So you want to pick the right one. 1 mole of CO2 gives us 1 mole of our product. So again, that's from the equation, and this is the wrong one. We don't need that guy. So could do the math there, I think. That's 2.272 moles of our product would be produced. And by the way, this would represent the theoretical yield. In moles, right? But since our actual yield was given to us in grams, we probably want to convert this into grams. So we would use the molar mass of our product, which again, if it wasn't given to you in that previous problem, you would go to the periodic table. And if we take that and times it by 60.06, gets us about 136.5 grams or 4, depending on rounding, of our product. And again, this would represent the theoretical yield in grams. Any questions on that calculation there? Now, we're not done, right? Because they wanted us to calculate the percent yield. So to calculate our percent yield, it is again our actual divided by our theoretical times 100%. Remember, our actual was given to us in the problem, which is 120 grams. Our theoretical we just calculated times 100%. Grams will cancel. And I think we're at like 87-ish, I think. About 87, 94%. excellent, but not too bad, I guess, but not the greatest. About 87.94% yield. Any questions on any of those steps there? So very often in a percent yield problem, you'll still have to do really a stoichiometry problem. And a lot of cases, it may be, again, a basic stoichiometry problem. Yeah, that's probably okay. It's just some rounding. I think maybe I'm just rounding a little bit differently today, and depending on your periodic table. But with rounding, it's probably okay. Basically the same. You probably just have to do a stoichiometry problem. Again, could be a basic stoichiometry problem where you don't have to worry about figuring out the limiting reagent if you're just given one piece of information. But again, if you're given the starting amounts of both reactants, then you will have to do a limiting reagent problem and make sure you figure out the theoretical yield, and the actual will typically be given to you. Any questions on this one? And again, on this one, what I'm going to do is I'm going to scroll through my kind of typed out version so you can, if you want later, take a look at it without all the scribbling. And again, I might round a little bit differently here as well, but it should end up basically the same deal. And it looks like we did. And I must have rounded better, just like you, Grace, there. I got 8791 there, as you can see. Any questions on how to do stoichiometry problems, limiting reagent problems, percent yield problems? The example that we skipped that's in the notes, the one that was before this, I'll tell you what you could do if you like. You could do it on a separate piece of paper and then take a picture of it and upload it. And I'll put an assignment up on Canvas for an extra credit assignment. And you could do that previous problem, which should be, try to do this without giving you the answer. Should be this one, I think. This is the one I think we skipped in the notes, if I'm not mistaken. Yours might actually say grams instead of kilograms. But you could do this problem that's in your notes, and it should come right before this one. And again, you can upload it onto Canvas. I'll put an assignment that's extra credit, and you can turn it in for some extra credit. Any questions on that? Yeah, the extra credit assignment is the one you're looking at on the screen. It's actually in your notes. It's in the notes. It should be the one that comes right before the problem we just did. So right before the problem we just did should be this problem, or one that looks just like it. Again, I think in your notes it may say grams, say kilograms, but it's pretty much this problem. You could do it and upload it, and it's not up there yet, so you won't be able to find it yet. But before today's over, I'll put up a little drop box, and you could drop in the extra credit, which would be this one that's on your screen, basically. Other questions on that? Okay, a couple of things. We'll take a little break like normal here. I'll open up the lab session in case you have questions. Today's lab is, we are going backwards, so I'm going to get the right number this time. I believe it should be 15 this time, and that should be the lead 2 iodide. Next couple of days, yeah. How about before Wednesday? Yeah, it'll be due sometime Wednesday, so you can turn it in sometime before Wednesday, okay? It won't be up there probably until later today, the box to drop it in. So the extra credit you could turn in by like Wednesday sometime, the end of Wednesday. So you're going to basically be doing what we're talking about here. There's like 3 different videos I think to watch. None of them are extremely long or anything like that, but it will show you what happens when you mix those two and what the yellow solid will look like. There will also be, and it's not up yet, I'm going to put it up in just a second, the lab. But there'll also be a PDF file or an image file in the actual page that contains information, some data, and you're going to use that data, put it into your table, and then that should allow you to do all the calculations for this experiment. Okay, so there will be some data that will be given to you, and you can use that data to do the calculations, and then you're expected to finish filling out the data table. You're also expected, again, a reminder to do the calculations in each of those boxes, and make sure when you do the calculations for this lab and all the labs that you show the work, the setup, the units, and everything. Remember that when you look at the table, the data table. When you look at that data table, there's certain entries that have little numbers, and those entries correspond to calculation boxes. 1 and 2. So obviously, whatever number you got here should be a result of a calculation, and you need to make sure that you show those calculations as well. So make sure that you show the calculations, finish filling in the table, and you also should be able to obviously do the post-lab questions as well. So the experiment will be due today. So again, the box will be open for you to upload it. And again, it will consist of the data table, the calculations all filled out correctly, and the post-lab questions. And again, there should be 3 links to a video. And then underneath those links, or you can watch the video on Canvas, underneath them will be the data table that you could fill in, or the information that you need. And now, since we completed pretty much this chapter, we're going to go on to gases next. You should be able to answer all the questions that are on there. Any questions on anything like that? So again, I'm going to take maybe a 10-15 minute break, and then I'll open up the lab session in case you do want to pop in and ask questions or something like that. I'll be happy to answer your questions. The lab's going to be due today. So I think I made it maybe like 5-ish or so. It's due officially. I think the box will be open until the end of today. So in case it's later than the due date, you can still submit it late. I don't know if I'll count it late, but the box will still be there for you to upload it. But try to get it in by 5-ish, yeah. Any other questions or anything like that? Okay, so we'll officially end the lecturing part. When we come back on Wednesday, we'll jump into the next chapter, which is, I think we're going to chapter 13, which is gases. So we'll jump into that next time. All right, I'll see everybody in a bit if I see you. If not, I'll see you on Wednesday.